In this video, we're going to pick up from where we left off in a related video where we developed a simulation model of a Subway restaurant in order to perform some basic verification analysis. So let's start by the system description first. Customers enter the restaurant and then they go to the first stage where they choose the type of bread and meat and cheese that they want on their sandwich. And then the customers go to the next stage, which is the oven. So if they want their sandwich toasted, uh, the worker puts the sandwich in the oven, and the oven heats the sandwich and toasts it. And then the customers will go to the third stage, which is the veggies station, where they put lettuce, tomatoes, and other types of vegetables and condiments on their sandwich. Once the sandwich is ready, the customers pay at the cash register, and after the payment is complete, the cashier puts the sandwich in a bag, and the customers then go to the drink machine and get their drink, and then they leave the system. The data that we're given are as follows. So the arrival rate is 32 customers per hour. The service times are all triangularly distributed for all of our 5 stages in our system. And the parameters of our triangular distributions are as follows. So for example, for the bread and meat station, the minimum is 1 minute, the maximum is 2 minutes, and the most likely value is 1.5 minutes. Similarly, for the oven, the minimum mode and maximum values are half a minute, 1 minute, and 1.5 minutes. The other thing is that not all of our customers want their sandwich toasted. So the data that we're given indicates that only 70% of the customers want their sandwich toasted and 30% get cold sandwiches. However, the current operating policy of this restaurant requires that we maintain first in, first out throughout the system. In other words, we do not allow customers who want cold sandwiches past the customers that are waiting for their sandwich to be toasted. As for the performance measures that we're interested in, um, particularly we want to evaluate server utilizations and also average time in system and expected number in system at steady state. So here is the initial model of the Subway restaurant that we developed in Simio in the related video. And as you can see, we have all of the parameters implemented, including the inter-arrival times and the expressions for our service times, and specifically for the oven station, in order to account for different processing times for cold and toasted sandwiches, we use a discrete probability distribution that we verified by running our model in the step mode. In order to further verify my model, I would like to compare it to an analytical model that I have developed. So here is my static queuing network analysis, and where I have estimated utilizations of my servers and number in system and time in system at steady state. So what I would like to do is run my model and compare these values together. So I'm going to increase the run length to 100 hours, and I'm going to run my model in the fast forward mode and then go to my results. And when I look at my number in system and time in system, I'm getting 5.17, and let me change the units to minutes here. So 5.17 for number in system, and average time in system 9.44. And when I compare these values to my static model, you will see that the values I get from my simulation model are much lower than my expected values. This difference is due to a couple of reasons. First of all, in my queuing model, I'm assuming that all processing times are exponentially distributed, which is not the case in my simulation model. Secondly, my queuing model assumes that everybody has the same processing time in the oven station. So basically my queuing model ignores cold customers. And finally, we know that from our simulation interactive run, we're only getting one observation of these random variables that we're trying to measure. So in order to get a better estimate, we need to replicate our model to get multiple observations. So now I'm going to make these changes, or basically modify my simulation model in order to make it correspond to my analytical model. And before I do it, I would like to save this model, and I would like to call it current policy. And now I'm going to change all my processing time distributions to exponential, and also I'm going to remove the discrete empirical processing time I have for my oven station, so everybody will have the same exponential distribution in my verification model for the oven station as well. So here is my modified model for my verification analysis. As you can see, I have changed all my processing times to exponential distribution with the same means. And of course, for the oven station, I have also removed the empirical distribution that I had. So now everybody is treated exactly the same on the oven station, similar to my analytical static model. So now, in order to replicate our model, I'm going to project home and create a new experiment. And I'm simply going to run my model for 10 replications and look at the results. So now the run is complete. I can go to my pivot grid and compare my values. So let me filter out the values that I don't need real quick. So I need the average in minutes, and percent values. And of course, the only data items that I need are number and system, scheduled utilization, and time and system. So now I have filtered my pivot grid to down to the performance measures that I'm interested in. So now I can go ahead and compare my values with my analytical model. So as you can see from my number in system, I'm getting 11.11, while I expect to see 11.4, 42. And for the timing system, I'm getting 21.06, while I'm expecting to see a little higher value of 21.42. So as you can see, it seems that our values from the simulation models, although our scheduled utilizations seem to be close to our expectations, but our timing system and numbering system seem to be lower than what we expect them to be. And that's mainly due to the fact that when we start our model, we have an empty system. So we start with 0 number in system, while at steady state, we expect to see 11.42 entities in the system. And also, for the first few entities, since we start with an empty system, we don't really expect them to wait in any lines in order to get processed. So for these entities, we expect their time in system to be much lower than what we typically see in at steady state. So in order to solve this issue, without getting into the theoretical and technical details, what we need is something we call warm-up period. So what I'm going to do is run my model for 300 hours, and I'm going to add 100 hours of warm-up period. So what the warm-up period does, it removes or deletes the statistics that we collect during the first 100 hours of simulation run. So we hope that this would help us remove some of this initial bias that we have in our results. So now when I look at my, let me reset and run my model, run my experiment again. So now I can go to my pivot grid and compare my values. And now, as you can see, I'm getting 11.8 instead of 11.4, and I'm getting 21.9 instead of 21.42. But when I look at the half-width, it seems that all my expected values fall within my confidence intervals. So now I have collected some evidence that my model is implemented correctly. And of course, if I would like to verify my model even more, I could either increase my number of replications to get more observations of my random variables. Alternatively, I could also increase my run length to hopefully get closer to steady state. And I could also increase my warm-up period to reduce the impact of the initial transient bias on my simulation outputs. So now that we have performed basic verification analysis for our subway model, I would like to talk about the general process of verifying a simulation model with an analytical model. So in general, we have a simulation model that we would like to verify, and our simulation model has a set of assumptions. For example, in our subway model, we perform a transient analysis, meaning that we are not interested in steady state analysis, but the performance of the system over a 12-hour operating day. Also, we have triangularly distributed processing times. On the oven, we have type-dependent processing times, and so on. On the other hand, we have a queuing model, which is our analytical model that we would like to use to verify this simulation model. But our queuing analysis has a different set of assumptions. In other words, our queuing analysis gives us the steady-state performance measures. And the assumption is that all processing times are exponential, and we have a single type of entity. So we cannot have type-dependent processing times in our queuing analysis. Since the assumptions of these two models do not match one another, we can't directly use our analytical model to verify our simulation model. So what we did in this video, we modified our simulation model such that the assumptions of the modified simulation model matches those of the analytical model. So in our modified simulation model, we increased the run length, we added warm-up period, and we performed steady-state analysis. We changed all the processing times to exponential, and we got rid of multiple entity types, and so all entities in our simulation model are treated exactly the same on the oven. So now that we have a simulation model that corresponds to our analytical model, we can use our analytical model to verify the modified simulation model. As an alternative approach, we could use another analytical model that corresponds to our original simulation model to verify our simulation model directly. Now, in this case, for our subway model, it was easier to modify our simulation model through making simple changes and use a simple queuing analysis to verify the modified simulation model. But again, the alternative approach is also perfectly valid as long as you can develop an analytical model that matches your simulation model. One thing that I would like to add here is that this alternative approach may not always work, especially for more complex models. We know that in general, analytical models involve strong simplifying assumptions to make the problem analytically tractable. So as the level of complexity increases, analytical models become less and less powerful to solve the problem, while simulation becomes a more attractive tool to perform the analysis. But in terms of the verification process, the idea is that in order to be able to perform comparisons between the simulation results and the results of an analytical model, the assumptions of the two models must match one another, and we can do this through the two approaches that we just talked about.